Okay, so like I said, the syllabus is available in Google Classroom, and this kind of gives you an overview of what we're going to cover. The required materials, like I said, the state has certain things that they're requiring us to cover in order for it to qualify as a foreign language. So that's one of the reasons that we're using this book. Computer Science Principles, the Foundational Concepts of Computer Science, 4 AP Computer Science Principles, and it says 2020 edition on the bottom. Does everybody that has the book already, does it say 2020 edition on the bottom? Make sure, because I know I had at least one kid that got one that was an older version. So this one's been updated and has more stuff that is kind of in line with what the state's requiring. So I want to make sure that you have the correct one. Does anybody, I know that you're still waiting on your book. Is anybody else still waiting on a book? Have you ordered it yet?
Yeah.
Okay, it has been ordered. Cool. Did I send you the PDF of it? Probably not. I think because Kate was the only one that I knew about. So let me make a note of that. Where's my marker? Tell me your name again. Isaac. Okay, so send Isaac. And it's just ISAAC?
Yes, sir.
Okay, send Isaac PDF for a book. It's not the whole book, but I just made a PDF of the reading assignment for this week. The way that you'll also need a laptop, so Windows or Mac. Windows, if you want to use the same system that I have, right? The same OS that I have, so it'll be a little easier to follow along. But Mac's okay. And then towards the end of the year, we're going to use an online textbook, eloquentjavascript.net. There's a print version in print, and if you like to have the print versions, you can get that. But it's kind of cool. They let you, like as you read through the book, you can do the exercises and actually code right there in the web page and play around with the JavaScript code. So it's kind of neat the way that they've got it set up. The way that we're going to do the course, the percentages as far as the grades go, is that your homework will count for 20%. And I should have put on there homework and class participation, right? So that includes your class participation. If you've ever had me in another class, you know that I like for you guys to interact with me. And so everybody by default has 100 on their class participation grade. So you know you're already in good shape as far as that goes. If you talk to me, right? If you interact with me and I think it's worthy, then I may add your name to the board. And if I add your name to the board, that means for that day, for that week, you just got an extra point for your class participation grade. So there's a possibility of every class, your name being added to the board. So instead of 100 at the end of the semester, however many classes we have, you may have 115 for that grade, right? And that's not bad, since it counts for 20% of your grade. So that's good to know. Class participation falls in the homework category. And you know, the homework things, there's not really homework listed in here, so that's going to kind of vary from week to week. There's a small one this week that I'm going to ask you to do as you read the section in the book. Weekly quizzes. I won't necessarily have a quiz every week, but we will have quizzes at the beginning of class, and that's just to reinforce the material that you've read in the book, so that when you take a test, you will have seen that material before, and just to kind of help keep these things in your memory. You know, it's another way for me to sort of check and make sure you're doing the reading with the quizzes. Only counts 10% of your grade, but still, that's an easy. If you do the reading, these weekly quizzes should be simple. I don't want them to ever be more than 10 minutes long, so it should be pretty quick. This first chapter especially is going to be, what we're going over today will primarily just kind of be definitions, right? So you'll be kind of matching up definitions, words to the definitions and so forth. There are bigger chapter unit exams that will count more. So we'll probably have those that'll be like at the, you know, we'll probably cover a few chapters together in that. I don't know, it depends on what the content of the chapters are. So those will count for more. And then the projects are really kind of the meat of what we're doing here. So that's going to include any kind of programming assignment that I give you. There are going to be some projects that we do in teams, right? So we're learning about computer science in general. And one of the things I want to kind of help you guys with is prepare you for potentially, if you enjoy this, working, you know, a professional workplace environment where you're working with teams in the computer science field. And so there are certain aspects of those teams that are pretty common, like with computer science, you typically have somebody that's doing the coding, right? So you've got the programmer, you've got or multiple programmers that are working on a project. You've usually got a project manager, which is kind of overseeing the project, talking to everybody and making sure everyone's on the same page. You've got a business analyst who is taking what the customer is asking for and kind of writing up the requirements and giving those to the programmers, for building the actual tool. You've got QA analysts, the people that kind of test whatever's built and make sure that it works like it's expected. So kind of what I would like to do is have some projects in the class where we sort of have a team like that, maybe a team of 4 or 5 people, where you guys will have an assignment and then you'll have different ones that function in one of those roles. And so some of the projects will be like that, where you'll have an opportunity to interact with one another and you'll actually be presenting something to us as a class, right? We're going to do, in a couple of weeks here, we'll start looking at graphics software. So you're going to have a project that's just related with creating something on that graphics software. And so there's an opportunity for you to exercise some of your creativity in that, or lack thereof. It's not one of those things where you're sort of judged on how creative it is, right? But it's more like judged on you using the tool effectively. So those are the 4 categories of grading. Anybody have any questions about that? Yes?
What other graphic software are we going to use?
So Photoshop is what I'm going to show you guys on my machine, because that's what the book covers. And but you got to have a license for Photoshop. And I looked all over the place trying to find like a student, some kind of student discount that I could get, so maybe I could provide a license to all of you guys, even if it was just for like a month or a couple of weeks, while we did that section of the book. But Adobe doesn't have anything like that. They do have a trial that you can sign up for, and it's only good for 7 days. So if you wanted to do that for your graphics project, it's like you'd have to sign up for it and get to work on it right away, and then you would lose it. Some people already have that though, so if you've got Photoshop, you can do that. You can use Photoshop for that. We'll talk about it more when we get on. Your computer comes with software already, right? It's going to be sort of rudimentary compared to something like Photoshop, but there's at least one free tool called GIMP that someone's told me about, and I'm going to try to do a little investigation on it. That may be something. I have already looked it up, and it seems to be. It's not like, it's not one of those things where you're just going to install a bunch of viruses. It's a legit piece of software. So you can use something like that as well. Does anybody have any suggestions, other suggestions for tools that are either cheap or free? For image manipulation? Okay, cool. Late homework is not accepted. That's the general rule, right? There may be some exceptions to that based on the illness or family emergency, but I expect you to turn homework in when it's due, and because that just makes more work for me, and it's more work for you, because you're going to have to get caught up, and then you're going to get behind, and you're going to do poorly in other things. So late work is not accepted unless there's some sort of excused absence that requires that. If you miss a quiz, like I said, when we do the quizzes at the beginning of the class, if you miss a quiz due to an excused absence, you don't have to make that up. You're just excused from that quiz, because I don't want us to have to fool with scheduling that. So don't worry about that if you happen to be sick that week. Chapter reading exams, blah, blah, blah. Yeah, projects include classroom presentations, collaborative assignments, coding assignments that span multiple weeks. Okay. All right, any questions in general about syllabus? Does that make sense to everybody? Yep. I keep kicking these things out of the, I should probably just take them off so it doesn't happen again. All right. Well, let's start going over the material that's in the book. And if there are no other questions. And you're welcome to look on in your book. I may refer at least to one chart that's in there. All right. So I'm going to sleep this because my battery's running low. I don't know if I'm going to need it. Like I said, initially, we're just going to be kind of going through material here, more definitions in this first chapter. So computers are absolutely everywhere today, right? They use them in children's toys, right? Vending machines. I mean, they're all over the place. You guys probably brought a fairly sophisticated one with you when you walked in the room as a cell phone, right? That computer is like a light years ahead of the early computers and what it's capable of doing. It's a very tiny, small form factor, right? So it's pretty impressive how far along computers have come. You know, I mean, a lot of us are wearing computers on our wrist with our wristwatches, tracking all sorts of things, and you can download apps and run those on there. So they're everywhere. 85% of Americans are carrying a computer with them when they carry mobile phones around. And those mobile phones are capable of doing things that originally when computers first came out, it might take like a 3-bedroom house to hold a computer that was that powerful, right? So that's a pretty significant difference. Can you imagine what used to take that big of a room? We are all just carrying them around in our pockets now, you know, so they've come a long ways. Early computers were full of vacuum tubes, and I was going to show you guys one of those. So here's a vacuum tube, about the size of your thumb, you know. And I'll pass this around, just try not to drop it, if you will, because I think it's still good. It goes in an amplifier of mine that's not working anymore. Oh, this thing says it's still on. Let's see. So they were filled with these vacuum tubes. The first substantial computer had nearly 18,000 tubes in it, right? So you can imagine the size of the building that would hold a computer like that. It had 18,000 of those guys in it. That was built in the 1940s, and that was the way the first ones ran. If you look up a picture of it, you'll see that there are. Oh, I do have some pictures on here. I do need to show you guys that. You see that there were like cables. You know, it's kind of like the old switchboard pictures where you've seen the ladies that sit at the switchboard. They flip out the wires. You know, that's kind of the way the computer would look as you were patching different things together, building these circuits that were full of all these vacuum tubes. Then we invented something called the transistor, and I didn't have a transistor to show you guys. I thought I did. I know I've got some at the house somewhere because we played around with those when I was in college. Transistor, this is always a dangerous thing. Let me unplug this just in case. It will be fine. Got it? Thank you, buddy. All right. So yeah, this is what a transistor looks like. So transistors look like this, right? You've probably seen like old circuits. My wife made me throw out an old, one of the old television, not the flat screen ones, but the old big ones, the cathode with the cathode ray tube in it. And if I'd opened that up, if I still had that, probably would find these all in it, you know. Back in the days of bulkier circuits. So you'd have these transistors, which basically replaced the vacuum tubes, and those came along in the 50s, and they helped with the size problem, right? You didn't have these bulky tubes anymore because these transistors are little, you know, they're probably about that big. But they had their own issues because all of these components were soldered to a board. So you have a little connection. Are you guys familiar with a soldering iron? Have you ever seen that? Where you've got this little kind of, I think it's aluminum wire. I can't remember exactly what the wire is made up of. But you heat this. You had this little iron that you would heat that up, and it would do a little drop of it would go down there, and you would be able to, you know, make that connection. Well, that solder would break. I mean, like I think now in the electrical world, they say don't solder anything because it's just kind of it's too easy to break. And so you had issues with circuits not working because a circuit would fail because a connection broke somewhere. So wiring issues were high. But then something came along, and what did I do with that? Here it is. In the 60s and the 70s, we had the introduction of the integrated circuit and silicon computer chips. So this is like one of the first phones that my wife had that actually had like a display on it, you know. I've got that opened up in the back, so just take a look at that and consider the size of that compared to these vacuum tubes, right? When you see the different connections on there, just imagine if you had to plug one of these guys in all of those connections, right? And what would be required to run something like that if it was made up of these vacuum tubes. So huge difference. Much smaller, right? Smaller, but faster. With these circuits here, the likelihood of wiring failing was very low because you didn't have, you know, actual wires that were coming off of it and had to be soldered together. So the size and the speed of the machines changed a lot. But the basic function of computers are the same function that the same thing that they accomplished when they were first created. And so I just want to kind of write down that basic definition of a function of a computer. Its basic function: it is an electronic device that processes data Oh, and by the way, you're welcome to take notes in your notebook, or if you're the kind of person that would rather just do them on your computer, I'm okay with that as well, as long as you're only using your computer for class-related stuff, right? So it processes data according to a set of instructions. Or commands known as a program. So that's the way they worked when they were first invented, and that's still a pretty good definition of a computer. It processes data according to a set of instructions or commands, and we call those instructions a program. So computers today, internally, they work with the same thing that they worked with way back when they were first invented, and that is they work internally with ones and zeros, right? Some of you have probably seen that movie that came out. I don't know, when did The Matrix come out? 90s, in the 90s, late 90s. Okay. So when The Matrix came out in the late 90s, and you'd see the kind of like the what was it, like a green color text? I'm colorblind, so I'm assuming it's like a green color. Is that what the color was, right? These zeros and ones going past the screen and all. Anybody? Did anybody not see either of these? Anybody want? Okay. But zeros and ones. Why zeros and ones? Because that's how computers think. All right. Underneath, when you pull back the hood and look at what's under the hood, they're dealing with basically electrical impulses, and with electricity, it's either on or it's off, right? And so the vacuum tubes, the early computers, these things would light up, and either they were on or they were off, right? You would plug the cables in, and you would complete the circuit. So either you would have electricity running through that particular circuit, or you wouldn't, on or off, right? And that's exactly the way computers still think today. It's still this idea of dealing with ones and zeros. So it's really what computers do is very basic. They're running these mathematical operations on very simple mathematical operations, but the power of computers is they can do a lot of those operations, and they can do them very, very, very quickly, right? Much faster than we can. And so that's what makes computers so powerful. Now, there are two basic components of computers that we need to be aware of. Two basic components. And those components are what we call software, and then what we call hardware. Somebody give me an example, or can someone give me an example of software when I use that term? Yes?
Photoshop.
Photoshop would be an example of software. Tell me your name. Isaiah. All right. Look at there. Isaiah, you are the first to get your name on the board. It feels pretty special, doesn't it? You guys could be experiencing what Isaiah is experiencing right now. He's trying to hold in the joy, but he's wanting to jump up right now. I'm just telling you, all right? Anybody want to give me another example? What about, so he said Photoshop. When we talk about our mobile devices, what do we typically call the software on there? Yes?
Like apps and stuff.
Apps, right? So like apps, tell me your name.
Justin.
Justin? So Justin's like, wow, I had no idea, Isaiah. That's pretty cool. So he knows now as well. So apps that we install, that would all be software. So software is stuff that we can't touch, right? There's no physical aspect to the software. It's the set of instructions that become those ones and zeros, right, that we're talking about that the computer understands. Like I said, it's really straightforward what a computer is doing. It's not particularly complicated behind the scenes. It's just that it's able to perform multiple of these simple calculations at incredible speeds. And so we can write software that does really complicated things because a computer can do that so quickly and can process so much information so quickly. So when we talk about software, so this can't be touched, right? Set of instructions or computer, that would be sort of definition, the general definition. And we kind of break software down into two categories. So we're gonna say A, we've got the operating system. And so somebody else besides Isaiah and Justin, because I don't want them to be the only ones to experience the joy. What comes to mind when I say operating system?
Linux.
Yes.
Like Windows or Linux.
Okay, I just heard someone else say Linux or Linux, right? You said Linux, right?
Yeah.
Okay, I've heard it both ways. I was just curious which one you guys would say. So Linux, and I think Linux is kind of like a variation on the old Unix system, right? So that's whenever I first started with computers, that's what we called it. That was before Linux kind of came around. So we think, you can think of Android for cell phones, or iOS, right? Or Windows, or Linux. There's all kinds of different, there are other operating systems out there too, but those are kind of more popular ones, right? And so what are operating systems responsible for? Who can kind of tell me some of the tasks that they sort of provide for us? Can you think of anything specifically? Yes?
Kind of taking the program's instructions that are installed and displaying it for the user and allowing them to interact with it.
Yeah, okay, so it's going to provide some level of some sort of default way for users to interact with the software, right? So like when you launch an app on your Android phone or your iPhone and you double tap that or single tap it, however it's configured, the reason that works, the reason that launches the app is because the operating system has been designed to work that way, right? So the I didn't get you guys' names on board. I totally missed that. So tell me your name again.
Adrian.
Eden, yeah. Eden's in 2 of my classes, and I still haven't gotten that down. And I can only remember that you speak on behalf of Hudson. That's all I can remember with you. Tell me your name again. Braden?
Yes, sir.
Okay, Braden. All right. Do you even know Hudson?
Yes.
Okay, all right, good. All right, so that's exactly right. It's lost my place here. Okay, so yeah, it handles requests between the hardware and the applications, right? So if the application is going to have to do something that's affecting the hardware, then the operating system is going to handle that for you. It includes device drivers, right? So like if you buy a new printer and you got to get that printer to work, there are device drivers that will allow that to work. It handles file management, right? That's a big part of what's going on your computer. You have to be able to write to the file system, create files, read from the file system. So the operating system is going to handle that. And just common services in general that are shared by other common services shared by other programs.
make myself a little more room here. So we've got the operating system, which falls under, one of the things that Aiden mentioned also, it has the user interface. So the GUI, the user interacts with, what does GUI stand for? Anybody know?
I thought it was pronounced GUI.
GUI? That's how you pronounced it?
Yeah.
Well, you tell me this, all right? Let's say, I'm going to count to 3, all right? And I want you to say what you just said, okay? 1, 2, 3. GUI.
GUI.
Do you see how fast I said GUI compared to GUI? Why would I want to say GUI, right? When I could just say GUI. It just like flows out. So GUI is how I learned it, right? That term's been around for years, and what it stands for is Graphical User Interface. So it's the graphical user interface that you interact with, right? Back in the day, when computers first came out, they were working with text. You just typed in everything, and before the days of having a mouse and being able to point and click and graphics and all that. So the graphical user interface was really a big part of what ushered in kind of a global adoption of computers, right? Because now the average person can interact with it and doesn't have to know how to write code or something like that. So yeah, you can say GUI, but I've always heard GUI, right? Let me see. Let me put that down there since I gave you a definition of that. Graphical user interface. And let's see. Anything else I want to say with that? So those are the pictures and the icons, right, that show up on your phone. And then the second type of software that we have is, those are the apps, right, the applications. And that's really all the rest of the software. Outside the OS. So that, that includes games, word processors, right, that we use, spreadsheets like, Microsoft Excel, calculators, music players, any other piece of software that we've got running on our devices would fall under the category of an application or an app. All right. So that was the first basic component of a computer, and so the second component, I'm going to need more room for this anyway. So, any questions about the software aspect of it? I always feel like you guys are kind of jealous that you don't get to do this, right? It's kind of like, that looks so cool. So what was the second basic component?
Hardware.
Hardware, right? So let's talk about hardware. And what falls under hardware? Well, under hardware, first of all, this is number 2, right? So you have what we refer to as the core components. And with our core components, that's the stuff that has to be there. Right? In order for the computer to function, this hardware has to be there. And when we say hardware, we're talking about the physical stuff, right? All the stuff that you can see and touch. So this includes, monitors and computer chips and your mouse and cables and printers, any of the physical stuff that's required for your computer to run. This is all the stuff you can touch, right? So for the core components, these are the things that the computer has to have in order to run, and we're going to give you just a handful of those. One would be your motherboard. He lists in the book that sometimes also called a logic board. That's another name that you may hear for a motherboard. And this is a motherboard. That's what a motherboard looks like, right? So it's got all of these different, weird slots and all here that are basically, there's a bunch of things on the side here. It's a bunch of connectors, right? A bunch of things where you can plug in other devices to the computer. So it's kind of the point at which everything is connected together.
it all happens with the other motherboard. It's the standardized printed circuit board that connects the CPU, the main memory, and all the peripherals, what we're going to call peripherals, and we'll define that in a minute, to your computer. So this is the standardized, and it's standardized because if someone's going to make a new piece of hardware, it's got to somehow plug in and communicate with the CPU and all. And so there's standard interfaces built into this motherboard, so that if you're building another component, you'll know that your component will be able to plug into the motherboard. So the standardized printed circuit board that connects the CPU, main memory, and the peripherals. Like I said, we're going to define these in a moment. Most of them contain a small integrated chip and firmware which stores the BIOS, which is the basic input-output system. Usually has a chip containing BIOS. BIOS stands for basic input-output system. And so if you've ever booted your computer up and have hit like F2 or F12, I'm always like hitting different function keys because I never can remember which one to hit. But your computer it won't go ahead and load Windows, right? The BIOS will load, and you can define all things like you can set the time for your device on there. You can define the boot order. So you can say, for example, if I stick a USB stick in my computer, I can say I want to try to boot from that first instead of booting from the hard drive. So you can specify things like that. So the BIOS is kind of what you use if you're installing the operating system from scratch. You got to have some way to do that, and the BIOS kind of functions as that. So there's a picture of a motherboard. Any questions about that? You don't have to know all these little pieces that are listed on there, but like it notes, it's probably hard for you to read some of this stuff. But this is where the CPU would go, which we're going to talk about in just a minute, which is like the brains of the computer. This right here is slots where you would plug in memory, right? So when you talk about how much RAM a computer has, that usually gets plugged in via slots like this. Usually there's, trying to see if there are some USB connectors on here somewhere. There's some input-output connectors up there. Looks like there's some kind of audio connection. This is maybe like an old printer, or that's probably a monitor, like a monitor connection up there. Where's USB? I know USB has to be on here. I'm not seeing it labeled. Right? Oh, and did you guys know that there's typically a little battery on your motherboard? They last a really long time, but like if your computer, I had a computer that it quit keeping the time. So every time I would shut it down or unplug it or whatever, it wouldn't maintain the time. And that's because this little battery in here died, right? Most of us, they don't get old enough to where we have to do that. But there's a little battery there that you might have to change out. Okay, so the CPU, that's another part of the core components. You got to have a CPU in order for the computer to work, and this is the brain of the computer. This is the part that's actually carrying out the commands, right? And the speed at which it processes these commands, speed usually measured. Who knows? How is it usually measured for a computer? So many what? Right now? Maybe if I write this down, you'll be able to tell me. It's usually measured in gigahertz. Yes, exactly. gigahertz, which is billions of processes per second. So that's, we can't keep up, right? Or there's no way we can match that. So like I said, the CPU plugs in like this area here. And so let me show you a picture of a CPU chip here. Here's one that's been, you can see it like both sides, right? So an Intel chip that you would plug in that area there. We also have main memory. So CPU is another part of the core component. Got to have that in order for the computer to function. You have main memory, which is also known as RAM, or random access memory is what that stands for. And so it's random access memory, let me say this, random access memory instead of sequential memory. So think of like a DVD or a CD versus an old tape recorder, right? Or reel-to-reel or something like that. You know, with the old tape recorders, you guys are so spoiled, you know. We used to have to sit there and I want to hear that last song on the tape. It's like you hit the fast forward and as it's going to the end, you know, and then finally it's played. See, I was not there yet. Go a little further and get to the song that you wanted. And then CDs came out and we just jumped directly to that track on the CD, you know. Now you don't have to fool with that, right? Just pull up a big long list on your device and play the song that you want to play with. But that's the way random access memory is more like a CD or a DVD, right? Where you can go to an exact spot. Say, go here and read from that area. Whereas with sequential memory, it's kind of like the tape deck. You have to kind of fast forward to the place that you want. And so for that reason, random access memory, or RAM, is much faster than sequential memory. So it's usually much faster than any kind of secondary memory on the system. But think of this data here as being volatile. Data is volatile. Does anybody know what I mean when I say the data is volatile? Anyone take a stab at that word?
Change.
It can change. It can change, but that's not what we mean in this case. But that was a good guess. Tell me your name. Isaac. What we mean by volatile is that it doesn't stay around when you turn the computer off. You lose that, right? So if you're in the middle of working on something and you want that still to be available when you power the computer back on, it's going to have to write it to some form of secondary memory, like your hard drive, right? So it might dump the contents of your RAM and write it to your hard drive on your computer, and then read it again when the computer boots back up. Whatever's in the RAM goes away whenever you shut the computer down. So think of that memory as being volatile. You load something in the RAM to work with it for the time that you're working on it, so it's much quicker. But you don't want to keep that cluttered up. You don't want to keep stuff there for long. So it's that stuff's constantly getting dumped. It's not permanent. So data is volatile, not permanent. Whereas whatever you store on your hard drive, when you boot up your computer, you expect that to always be there. That's why you lose your unsaved work whenever your computer crashes, right? You're in the middle of doing something. Always save often. Man, I remember that happening one time in college. I don't remember what I was working on, but it was huge paper. And my computer crashed. And now, at least most of the time, like if you're working in Word, it tries to do like an autosave, right? In the background, it keeps a copy. But that was before the days of autosave, and I lost every bit of that work. I had to learn that lesson the hard way. But that's why, because the copy that I was working on, I was working in RAM, right? The computer crashed, and I lost everything that was in RAM when the computer came back up. Generally speaking, if you increase the RAM in your computer, you also increase the speed of your computer because it can load more stuff in there to work on temporarily, and because it's so much faster. And then the last thing that we have is the power supply. This is the last piece of what we call core components.
And this is, of course, like a power adapter on any other device. Power adapter that converts AC power to the lower DC power used by the computer. Usually includes a fan, keep it cool. All right, so these are all the components that we say are necessary for the computer to work. Everything else is extra, right? These are the only pieces that have to be there. Now, there's a lot that's missing from this as you think about the computer that you work on. What kind of pieces fall under the category of hardware that you're? Well, let me show you a power supply real quick. I got RAM on here too. So here's a piece of here's some RAM that it might look whenever you buy it. In the store, buy it in the box, and here's here's a piece that's installed on the motherboard, right? So I showed you those slots on the motherboard, and you just take that stuff and you literally plug it in. So if you've never replaced RAM on your computer system, that's generally very, very easy to do. And if you're having trouble with your system being slow, that can sometimes be an easy way, a relatively cheap way to get more bang for the buck. And then, so speed things up, make it a little quicker. And then power supply, this is what a power supply might look like. And you can see all these connectors over here, right? This is all stuff that's going to be plugging in your motherboard. Or other devices may be plugging into that as well. But we saw a whole bunch of different places where things connect on the motherboard. Any questions about hardware in general and what we specify, what we define as core components? So what's missing? What things are not included in that we use on computers all the time that fall under the category of hardware? Graphics cards, right? Those aren't absolutely necessary, right? The computer can still do a lot of work without us being able to see anything. The graphics cards are for us to see things, and so that means monitors, right? That's not a necessary item on a computer to be able to do its job. There are a lot of computers that are doing stuff that there's no monitor hooked up to it. Yes?
Mouse count? I've used a computer when my mouse broke without it.
So mouse, again, I don't need a mouse. It is not under the core components, right? So all of these things that you're listing, keyboards, these are things that we define as peripherals. So these are necessary, and these are optional. As far as a computer goes, for the basic function of the computer, for it to do its job, everything else is necessary. Now, I understand, depending on what you're doing with your computer, a particular peripheral may be essential to what you're doing. But I'm just saying, as far as the computer in general, it can process stuff. The CPU can work just fine. The main memory function just fine. As long as it's got power, right? And you don't have to have all that other stuff. It's just your particular use case that requires the other things. So everything else, right? Everything else defined as hardware. So this includes secondary memory. And what would be some examples of secondary memory? Anybody tell me?
Hard drive?
Who said that? Okay. Hard drive. What's your name? Josh. Okay. Trying to remember. Got a lot of kids' names. Hard drive, right? Another example of secondary memory? Yep.
SSD.
SSD. I'm just going to do that all lowercase. SSD. So what does SSD stand for? You know?
I don't know.
SSD is also an excellent way to make your computer work faster. If it's moving slowly, you have the old hard drive. SSD really kind of functions as a hard drive, but it's much faster than the old traditional hard drives that were spinning around and had a bunch of moving parts. Tell me your name again, buddy.
Howie?
Howie. So SSD stands for solid state drive, and it doesn't have any moving parts. It's just kind of like that thing that we looked at on the cell phone. There's nothing that's moving, so it's a lot faster. Does somebody have something else that would be considered? What about USB drives? You plug those in, right, to your computer and store information on that. So USB drives or thumb drives, those would all be the types of things that would fall under the category of secondary memory. And then we've got input-output devices, and that would be stuff like, or you might define that I/O. That's what I/O means. I/O devices. When I've taught this before, I've had kids think that that was 1-0. That's not 1-0. That's I/O for input/output. All right. So I/O devices such as keyboards, mice, microphones, mics, printers, monitors, speakers, as we talk about those keyboards, would that be an input or an output device?
Input.
Say that again?
Input.
Input, yes. I couldn't tell. There were a couple people talk. So, yes, that would be input. Keyboards would be inputs. Mice, input. All right. You're putting information in the computer. Mics, input. Printers, output. Right. Monitors. Does everybody agree?
Unless kind of
What?
could be a touchscreen monitor.
Could be a touch screen. So monitors could be input or output, depending on the type of monitor, right? And then speakers, that would be output, right? So very good. All right, let's talk about how we do it on time. 3:13. Cool. Let's talk about number systems. We have how many? This is not a trick question. We have how many digits on our hands? Come on, guys. How many digits do we have on our hands? 10. We have 10 digits on our hands, right? And so we typically use a number system which is called a base 10 number system. So base 10 number system, that's what we grew up learning. Number systems. Base 10 or decimal. Number system. Is what we learn as kids and what we use every day, right? That's what we're typically working with in our math classes. It's base 10 number system. We use 10 numerals. It's base 10 because it has 10 numerals. What 10 numerals do we use?
1.
1, he said 1, 2, 3, 4, 5, 6, 7, 8, 9.
Not 10, it's 0.
0, there you go, there you go. All right. So I won't put the 0 down here, right? I'm gonna put a slash to it so we can distinguish the zeros from the O's. That was close enough. Your name's already on the board though, right? All right. So exactly, right? 0 through 9. That was a trick question, so you fell into my trap. All right, so that's how we define our numbers. We use those 10 digits, right? Those 10 numerals. But numbers, they don't think that way. What did we say numbers think in?
Binary zeros.
Binary. Wow, he just went on there. He just took it all the way to binary, right? Was he ready for that yet? Can we just pretend we didn't hear that, right? Computers think in zeros and ones, right? Just two numerals. And so just like a bicycle has 2 tires, the computer number system, the one that computers use at their base level, is called the binary number system. Very good. Binary number system. Or base 2. And you could write it with the number 2 or the number, just like with the base 10. It could be base 10, and you could write it base 10. All right, so that's how computers think. And so for a computer, so like if we write a number, it could have any of these numerals in it. But if we write a number in the binary system, it can only be a 0 or 1. And so we call a single numeral in binary. Does anybody know? It's 3 letters.
Hex.
Huh?
Is it hex?
No. Has anybody ever seen the movie Tron? There's a little thing in Tron that says yes, no. You just kind of yes. No, hold on.
Is it a bit?
It's a bit. That's it. A bit. So a single numeral in binary is called a bit. Tron takes on a whole new meaning when you watch it after you've learned some stuff about computers. So it's called a bit, and we can think of that as a bit can be 0 or 1. It can also be thought of as no or yes, false or true. Whoops. False or true, off or on. Right? So those are all ways that we can kind of think of. It's just 2 values and different ways that you might think about those values. A bit's really small though, and so typically we group bits together. Typically group together into 8 bits, which is called, anybody know? 4 letters, yes?
A byte?
A byte, thank you. So a bit and a byte. And so when you're looking at information that you're storing in a computer, each address in a computer's memory contains 1 byte of information. So that's kind of the way to think about that. And computers today can store a lot of information, right? It's huge compared to what they were when they first came out. We don't usually talk about bytes anymore because the byte's so small and our computers can store so much more. So there's a chart on page 30 in the book, and I'm not going to go there for time's sake, but, well, let me just write this out very quickly. Just some of it. So here's the unit. So we have a byte, and we have a kilobyte, and this give you some frame of reference, a megabyte. What comes after megabyte? Gigabyte. And now we have terabyte drives. Wow. Whoever thought we would be able to purchase something like that would be affordable. So the actual number of bytes that you have when you have a byte. This is in exponent form. Exponent form. Since it's a base 2 system, since binary is a base 2 system, then you think of all of these numbers as 2 to some power. All right. So when you talk about 1 byte, that's 2 to the 0 power, right? Because anything raised to the 0 power is 1. So this is this is decimal form here. So number of bytes. So that's just 1, and the approximate number would still be 1 with that. For a kilobyte, it's 2 to the 10. So when we talk about a kilobyte, we typically think of kilo as representing 1,000, but in computer terms, it actually represents 1,024 because that's what 2 to the 10 is, right? And so the rough approximation would be 1,000. But that's not actually how many bytes it is. With megabyte, that's 10, 2 to the 20, so it's 1,048,576, and so it's roughly 1 million. And it just goes on and on. This is 2 to the 30, this is 2 to the 40, so you can punch that in your calculator and see what the actual numbers were there. But it's roughly 1 billion, and here it's roughly 1 trillion. And so you may want to check out the packaging next time you buy something that's measured, a card that's measured in 64 gigabytes or 128 gigabytes or something like that. It could be that the manufacturer is using the approximate term. So when they say they give you 120 gigabytes, they may be giving you 120 million, when really, if you multiply this times 120, it's quite a bit more than that. So you may be cheated depending on which manufacturer you purchase from. So that's just something to be aware of. Any questions about that? I really want to walk through converting from binary to decimal, but we're kind of up against the clock. Let's see. Let's just introduce this topic and we'll see how far we get. So when we write numbers in decimal form, we may not really think this, but decimal is a base what system? Base 10 system, right? And so we think of this as the ones place, right? And this is the tens place, and this is the hundreds place, right? If we write a number like 352, well, that's 10 to the 0. Oops, not 10 to the 1. 10 to the 0 is the ones place. This is 10 to the first power, right? The tens place, and this is 10 to the second power, and so on. So as you kind of went up, if you wrote a bigger number in decimal form, be 10 to the second, and then 10 to the third would be the thousands place, and then 10 to the fourth would be the 10,000s place, and so on, right? Does that make sense to everybody? So if we wanted to, we could take 352, and we could say that 352 is equal to 3 times 10 squared, so 3 times whatever's here in that place, plus a 5 times whatever is in this place, 10 to the 1, plus 2 times whatever is in that place, the 10 to the 0 place. So if we multiply those out, this would be 300 plus 50 plus 2. And when we add all that together, we get 352. Okay? We just kind of do that in our heads because we're so used to thinking about working with base 10 systems, right? But this is the same way that you need to think about binary system. All right? And so if we have a number like this, 1, 0, 0, 1. Binary is a base what system? Base 2, right? So this then is the 2 to the 0 place. This is the 2 to the 1 place. This is the 2 to the 2 place. And this is the 2 to the 3rd place. And so on. All right? And so if we go ahead and do the math with each of these, 2 to the 0, let me actually put that on the top here so we can keep up with it. 2 to the 0 is 1. 2 to the 1 is 2. 2 squared is 4. And 2 cubed is 8. And so on, right? It would double each time. 16, then 32, and then 64, and so on. And so if I want to see what this number is in decimal form, then I would do the same thing I did here. I would say in decimal form, then that is 1 times 8. We're going to go ahead and do the time, the 2 to the 3rd. We've already converted that to 8. 1 times 8 plus 0 times 4 plus 0 times 2 plus 1 times 1. And so basically any of these with 0, they just kind of go away. And so we've got 8 plus 1. So this number, this binary number in decimal form is the number 9. So that's how we would convert from binary to decimal. Have you guys seen that before? I didn't know if any of your math classes, if you've ever been exposed to that. Is that kind of brand new for you? All right. So I want you to be able to do that. And there's some examples in the book. If this is a decimal number, though, what would that number equate to in, if this is a binary number, what would that number equate to in decimal form? If this is the ones place and this is the two place, then it would be 1 times 2, which equals 2. So this number in binary equals 2 in decimal, right? And so I say all of that because now, if you guys ever see some nerdy person wearing a shirt that says this, now you can get that joke, right? Some of you are getting it anyway, right? This is a binary number, so there are actually two types of people in the world: those who understand binary and those who do not, right? So if you walk past someone and you snicker when you see that shirt, they'll be like, "Oh, fellow nerd." All right, guys. For class this week, all I want you to do for homework, and I'm going to load this in Google Classroom so you'll see it, but you're just going to read through the book, read pages 23 through 50, 23 through 23 through 31. And I want you to do this. Email me. I want you to email this to me. Email me one paragraph based on one topic in that section. Research further online. All right, so I want you to pick a topic. I want you to find out more about that topic than what's listed in the book. And I don't want this to be a big writing assignment, but I want you to just write me one paragraph with some meat to it, right, about something interesting that you found out about that topic.
Because a big part of computer science is researching stuff online, okay? And also a big part of computer science, if you ever work in the professional world, you're going to have to be able to communicate effectively, right? So this is kind of also an opportunity for you to show me what your communication skills are in effectively communicating that information to you, okay? Does anybody have any questions about homework? Yes?
Do we need to put our reference in the email?
Yeah, let me know where you, good point. Yeah, list reference. List reference or references. All right, that's it. Let me know if you have any questions. You guys have a great day.
Yeah, give that to me.